How many binary digit strings are possible of length n? You must have encountered this problem in the earlier videos or of earlier weeks, but let us see how to solve this giving a recurrence relation flavor. Now, the question is, how many binary digit strings are possible of length n? So you know that binary digits are only 1 and 0, so how many strings can you form of length n using these two digits? Now, consider this to be a string of length n. So this is an n bit string. Now, I will represent the length of this as, or rather t of n I will write it as the number of binary digit strings of length n. So if t of n is the number of binary digit strings of length n, then in case I write a 0 here, then this would become an n minus 1 string, that is n minus 1 bit string, right? So in case I write a 0, the rest of it is of length n minus 1. And then t of n minus 1 would represent the number of binary digit strings of length n minus 1. Now, wait a minute, let me explain things more clearly. What did we do initially? We took a string of length n, then I represented t of n to be the number of binary digit strings of length n. Now, in case, so if I start this with 0, the rest of it is of length n minus 1. So the number of ways of writing strings of length n minus 1, I'll represent that as t of n minus 1. Yes, this is the progress so far. Now, in case I start the n-bit string with 1, still the rest would remain as t of n minus 1 itself. That is, the n-bit string can start with either 0 or 1. That's what it means. Now, how did I write it as t of n minus 1? Of course I can write it because this bit string of length n minus 1 is independent of what is happening initially, right? It's not dependent on this and hence it can be written as t of n minus 1. Now, so I wrote the n-bit string and then I broke it down into two pieces with starting with 0 or 1, and the rest of it I can represent it as t of n minus 1. Now, writing it in terms of an expression, t of n as t of n minus 1, you see why I'm writing it twice here? 1 represents the n-bit string starting with 0 and the rest of them of length n minus 1, or the other case is n-bit string starting with 1 and rest of them can be written as t of n minus 1. You see, by rule of sum, there is a plus here. Why? Because either this is possible or this is possible. You start the string either with 0 or with 1. One of them will hold true, right? And hence, t of n can be written as 2 times t of n minus 1. Now, this is the recurrence relation for finding the number of possibilities of n-bit string. You must be remembering this. We have done this even in the functions chapter as well as in the set theory chapter. You might want to revisit that and warm up your mind for it. Now, how do I calculate this? This is the recurrence relation. We must find a solution to this. So, t of n is 2 times t of n minus 1. But to calculate t of n minus 1, I require t of n minus 2. Now, to calculate t of n minus 2, I require t of n minus 3. For this, I require t of n minus 4. And so on till the end, which is t of 1, right? T of 1 would be 2 times t of 0. But how do we calculate t of 1? Till now we have broken t of n as 2 times t of n minus 1. Now to find t of n minus 1, we need t of n minus 2, we need t of n minus 3, and the process continues till t of 1. But we can definitely find out T of 1. How can we do that? What does T of 1 mean? T of 1 means the number of ways of writing one bit string, which means the string should be of length 1. If it is of length 1, I can put a 0 here or I can put a 1 here, which means there are only 2 ways. So T of 1 happens to be 2. Given this information, we can see that T of 1 is 2. Now, T of n is 2 into T of n minus 1. We know this very well. T of n minus 1 can be further written as 2 times 2 into T of n minus 2. How? I can just assume the logic which I have done so far, because I have proved to you that T of n equals 2 into T of n minus 1 is true. Right? We have seen that. Again, you consider a string of length n minus 1. In the first place, you either started with 0 and the rest is n minus 2 length. You started with 1. Again, you obtain the same thing, that T of n minus 1 is 2 times T of n minus 2. Now, this can be simplified as 2 square T of n minus 2. Now, T of n minus 2 can further be written as 2 square into 2 times T of n minus 3. Right? In a simple way, this can be written as 2 cube into T of n minus 3, and so on. This process will continue. But where will we end it? We can write it as, observe these 3 steps before we continue. 2 into T of n minus 1, 2 square into T of n minus 2, 2 cube into T of n minus 3. Do you observe the pattern here? I had told you to observe this before we continue. There was a reason for it. When you observe this pattern, you can see that T of n can be written as 2 power k into T of n minus k. Right? This is the general expression. Now, T of 1, we know that it is 2. Right? So, if I substitute n minus k as 1, why? In the previous step, we had seen that T of n can be written as 2 power k into T of n minus k. We don't know what n minus k is. We do not have the knowledge of it. But we definitely know that T of 1 is 2. Now, if n minus k happens to be 1, then k is n minus 1. This is simple math. So, in place of k, if I substitute n minus 1, so at this point k equals n minus 1, T of n happens to be 2 to the n minus 1, because it was 2 to the k earlier, you remember? So in place of k I have substituted n minus 1. So T of n happens to be 2 to the n minus 1, T of 1. And we know what T of 1 is. Therefore, this is equal to T of n minus 1 into 2, because T of 1 is 2. Right? Now, simplifying this, we get it as T of n is 2 to the n. Now, T of n is 2 to the n. This is the final solution for the recurrence relation, where we were finding out the number of ways of writing an n-bit string. Keep this in mind. We will further see a variation of this problem. This was to warm up your mind.